Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion for Physics 151 and Physics 201. We've been talking about Galileo's dialogues concerning two new sciences. We started last time talking about day 3 of his dialogues, where he introduced the concept of uniform motion. You might recall uniform motion is motion in which an object travels equal distances in any equal intervals of time. So another way of saying it is that the rate of change of position is constant. So if you are a little bit confused about that still, you might want to look back at my last lecture. We arrived at about page 107 in A Student's Guide to the Great Physics Text, volume 2. And on page 107, Galileo is drawing out some of the implications of his definition of uniform motion. I want to run through these kind of quickly before we make our way on to uniform acceleration. So you can see on page 107, he has some axioms. He says, for example, in axiom 1, in the case of one and the same uniform motion, the distance traversed during a longer interval of time is greater than the distance traversed during a slower interval of time. So what is he saying here in axiom 1? Axiom 1, he's saying if one has uniform motion, that is, something is moving at a constant velocity v, or a constant speed. And you might think about it this way. If you have two objects, both of which are in uniform motion, let's say the velocity or the speed of the first object is equal to the speed of the second object. Then he's saying if you consider two different amounts of time, so if you're considering a certain time that object 2 is moving, and that time is greater than the one under consideration for object 1, that implies, or then, the distance that object 2 moves is going to be greater than the distance that object 1 moves. Again, so if you think about two objects moving such that they have exactly the same speed, then if you think about some time interval t2 that this one is moving and another time interval t1 that this one is moving, and if t2 is bigger than t1, then the distance that the second object moves is going to be bigger than the distance that the first object moves. Okay, so this might seem obvious to you, but he's just spelling out these implications. And likewise in axiom 2, he says that in the case of one and the same uniform motion, the time required to traverse a greater distance is longer than the time required for a lesser distance. So in that case, he's saying if the two speeds are equal, then if you're considering a greater distance, it requires a greater amount of time. Okay, and likewise, similar kind of things for axiom 3 and axiom 4. I don't want to spend too much time going over those. You can look at those if you like. He also mentions theorem 4, proposition 4. So this reads a little bit like a mathematics book, right? And here I'll just briefly say, and I'm not going to go through the proof, I'll just mention what he's talking about. He's saying if you consider two particles or objects, two particles that are both in uniform motion, but they have different uniform motions. So they're traveling at different speeds, but different uniform motions. And you want to compare their motions, the distance that object 2 moves. If you want to compare the distance that object 2 moves to the distance that object 1 moves, it's in a compound ratio formed from the ratio of the velocities of the two objects and, or multiplied by, the times that both objects move. So again, this is kind of how Galileo describes how he writes out mathematical equations. He forms these ratios. If you want to compare the distances, you have to compare the speeds and the times. The way we typically do this today is we say that the distance an object moves when it's in uniform motion is its speed times its time, or distance is velocity times time. Again, this is not how Galileo writes it, because he, inheriting this Greek system, or the ancient system of doing mathematics, he's uncomfortable with multiplying unlike quantities. In this case, we're multiplying a velocity times a time. He would rather form a ratio of distances and equate those to a ratio of speeds and a ratio of times. So that's what he's doing here. And then he goes through a proof of this in that long paragraph on page 107. I will not spend any more time talking about that. All right, now let's go on to talk about naturally accelerated motion. This is on page 108. And I'm going to read a few segments here and then comment on it. So he begins by saying, the properties belonging to uniform motion have been discussed in the preceding section, but accelerated motion remains to be considered. And first of all, it seems desirable to find and explain a definition best fitting natural phenomena. For anyone may invent an arbitrary type of motion and discuss its properties. And then he goes on to say that people have invented ways of discussing very complicated types of motion, but that he is interested not in just defining arbitrary types of motion, but defining an actual motion that occurs in nature. He says, we have decided to consider the phenomena of bodies falling with an acceleration such as actually occurs in nature, and to make this definition of accelerated motion exhibit the essential features of observed accelerated motion. And this at last, after repeated efforts, we trust we have succeeded in doing. In this belief, we are confirmed mainly by the consideration that experimental results are seen to agree with and exactly correspond with those properties which have been, one after another, demonstrated by us. Finally, in the investigation of naturally accelerated motion, we were led by hand, as it were, in the following habit and custom of nature herself, in all her various other processes, to employ only those means which are most common, simple, and easy. For I think no one believes that swimming or flying can be accomplished in a manner simpler or easier than that instinctively employed by fishes and birds. So what is Galileo saying here? He's saying that he's interested in understanding the motion that dropped objects actually undergo. And he's convinced that he's been able to figure out that type of motion. And he's going to say that is uniformly accelerated motion. And he'll define that in a moment. But I think it's interesting here to see his reasoning why he thinks he's been successful. First of all, he says that by looking at nature, the definition that he is going to describe shortly is matched by experimental results. When you do this in a laboratory, you'll see that he's correct. And secondly, because it is a very simple kind of motion. And he likens it to the kind of way that birds fly or fish swim. He's saying that there's a nature or a type of motion that birds or fish naturally undergo, and also there's a type of motion that dropped objects naturally undergo. So why is this significant? I think this is interesting because he's really coming out of this ancient and medieval view of how nature works. And he isn't yet at the point where he's adopting the very modern view. What do I mean by that? Well, the modern view, think about gravity. The modern view, and we'll get to this later on in the class, is that, and this is the Newtonian view of gravity, that rocks or the moon or other kind of objects are inert in a sense. They don't have any active properties. Rather, there are these laws imposed from the outside by God or someone else. There are these laws imposed on nature, which itself is inert, but the universal law of gravity that Newton's going to describe is something that God basically instills upon or governs nature by dictating. That's a little bit different than the way that Galileo and the medievals and the earlier thinkers were understanding this. They understood that rocks fall down to the earth, but it's not because of some law imposed on it from the outside. Rather, it's because things have certain natures kind of built in or innate to them. Okay? And so rocks fall because it is their nature, their inherent nature to do so. It's sort of built into the rock itself. That's how Galileo and the earlier thinkers are understanding gravity. They're using the same term gravity that Newton will later use, but they're philosophically thinking about it a little bit differently. He goes on then to say, when therefore I observe a stone initially at rest falling from an elevated position and continually acquiring new increments of speed, why should I not believe that such increases take place in a manner which is exceedingly simple and rather obvious to everyone? If now we examine the matter carefully, we find no addition or increment more simple than that which repeats itself always in the same manner. This we readily understand when we consider the intimate relationship between time and motion. For just as uniformity of motion is defined by and conceived through equal times and equal spaces, thus we call a motion uniform when equal distances are traversed during equal intervals of time, so also we may, in a similar manner, through equal time intervals, conceive additions of speed as taken place without complication. Thus we may picture to our mind a motion as uniformly and continuously accelerated when, during any equal intervals of time, whatever, equal increments of speed are given to it. So there he's presenting his view of uniform acceleration. So let me describe this mathematically. What he's saying is that dropped objects undergo this simple motion, and this simple motion is one where they undergo uniform acceleration. What does he mean, or how does he define uniform acceleration? He says that equal increments of speed are acquired by the object or particle or whatever is undergoing uniform acceleration during any equal increments of time. Notice that this statement is structured a bit like his statement of uniform motion, but it's slightly different, okay? Whereas maybe I'll draw first of all, uniform motion is equal increments of distance are acquired in equal increments of time. So if I broke time into equal increments like this, during the first interval of time, a certain amount of distance is traveled. During the second interval of time, the same amount of distance is traveled. During the third interval of time, the same amount of distance is traveled. So if you were to plot the distance versus time, there'd be a linear relationship between distance and time. This is what he meant, or how he defined uniform motion. What about uniform acceleration? Well, now he's talking about how speed is gained. So if we think about speed as a function of time, if you consider equal intervals of time, during every equal interval of time, equal increments of speed are acquired. So during the first interval of time, a certain amount of speed is gained. During the second interval of time, the same amount of speed is gained. During the third interval of time, the same amount of speed is gained, and so on. So there would be a linear relationship between speed and time. This would be the case of uniform acceleration. Okay, so that's how he distinguishes uniform motion from uniform acceleration. All right, and again, this is interesting how he arrives at this. He's likening falling objects to having a nature that tends to undergo this simple motion. That's the essence of that thing. And he kind of compares it to living organisms. Living organisms like birds and fish undergo a motion that is appropriate to their nature or their essence. Likewise, dropped rocks undergo a motion that is appropriate for their nature or their essence. Okay, so I'm going to stop here. Next time I want to talk about some of the objections that Segredo and Simplicio bring up that challenge this description of naturally accelerated motion that Salviati is here presenting.